Let's say that we have a displacement equation as follows. X t equals 7 centimeters times cosine of 5 radians per second multiplied by t plus 2 pi over 9. And this is our displacement equation. Now, if you might be able to tell, this equation is modeled directly after this one. A times cosine of angular frequency t plus 5. This is the displacement equation for simple harmonic motion. And essentially what we're going to be doing today is taking this equation and finding a ton of different stuff about it. For example, we'll find period, we'll find max velocity, max acceleration of this oscillation. We can find displacement, we can find velocity, we can find acceleration at a certain time interval. So, sit back, relax, and let's do some physics. So, the first thing we're going to do is we're going to find angular frequency. Angular frequency, this is A. Angular frequency, if we look at this equation and compare it to the first equation, angular frequency seems to be 5 radians per second. So we'll write it right down here. And this is angular frequency. And angular frequency is denoted by omega. Now for B, we're going to find frequency, not angular frequency, just frequency. Now the equation for that is F equals omega over 2 pi. So now that we know omega, we can just do 5 divided by 2 pi. And that's our answer. In order to keep it as a more exact value, we're just going to end here. Our answer is 5 over 2 pi. If we simplify it, we're going to get a long decimal answer. And I don't necessarily have a calculator on hand right now. So this is F. Now for C, we're going to find the period. Now the period is opposite from frequency. So the period is denoted by T, and that is going to be 2 pi over angular frequency. The reason that we're multiplying and dividing by this number 2 pi is because 2 pi is the amount of radians it takes to complete a full revolution. So if you start at one point here and you go in a perfect circle, which that was far from perfect, but it'll still do, then to travel around this entire circle and end up back at where you started, we'll take 2 pi radians. So that is how we are achieving all of these values here. So to find the period, we're going to take 2 pi and divide by 5. And then that will give us t. And let me make this clear, I'm not subtracting by these values, I'm simply just pointing out that this is the value we found. So it might be helpful to do a little parentheses instead, just saying this is period, this is frequency, and then this is omega. This is angular frequency. Alright. D, we are going to be finding the spring constant. So the spring constant is K, and K equals M omega squared. Why is this the case? Well, angular frequency is equal to square root K over M. So if we want to solve for K, then we have to square both sides to get rid of the square root, and then we have to multiply by M on both sides. So when K is alone, we have mass times omega squared. Just like that. So that's how we got that value. So now I should have prefaced this by saying that our mass here is 0.2 kilograms. So 0.2 times 5 squared. That's 25 times 0.2. That's 10. Now I think we can fit one more before moving the camera and erasing some stuff. So E here. For E, we are going to solve for the max velocity that this oscillation can reach. What we're going to do is we're going to take the amplitude up here and convert it to meters. So it's going to be 0.007, and we're going to multiply that by angular velocity, because another thing to note is that V max here equals A times omega, which this is equal to 0.07 times 5. Now the answer to this, I believe, probably be like 0.035. So max velocity would be 0.035 meters per second. And then this is V max. Now, to find max acceleration, for F, max acceleration is going to be equal to A times omega squared. So AM equals A times omega squared, like so. So this is going to equal 0.07 times 5 squared, which 25 times 7 is 175. So therefore, this answer is going to be 0.175 meters per second squared. This is going to be A max. I apologize for My handwriting was a little sloppy there. Actually, I apologize. It's going to be 1.75. Not 0.175. That should be the right answer now. So now for G, what if we want to know the phase? Well, the phase is simply everything inside of the cosine function. So everything multiplied by cosine is the phase. So if you remember, in our original equation, we have cosine 5 radians per second times t plus 2 pi over 9. Everything in parentheses here is going to be the phase. So suppose we want to find the phase at t equals 2. All we have to do is, and then it's going to be 5 times 2 plus 2 pi over 9. Whatever this is equal to is your phase at t equals 2. Now, let's say we want to find velocity at a specific point. Well, going back to this original equation, this equation is position. So, if you take the derivative of this position equation, you will get velocity. So, to do that, for h, a is a constant, so a, to get v over t, a sits out front because it's a constant, and then you want to take the derivative of cosine, which is negative sine, and then you don't do anything with the inner function, you just rewrite it. And then because of chain rule, you will actually get an omega out here. Multiply that by omega. I realized I accidentally plugged in values here. So if we're going to smudge what we have here and write over it, this should be omega t, and this should be phi. So here is our derived equation for velocity. All you have to do is plug in the original values here, and then let's say we want to find it at a specific point, so t equals 2. You just plug 2 in wherever you see the t's. And since I'm running out of space here, I'm just going to leave it as this. This is the velocity equation. And simply, all you have to do to find the velocity at a specific point is plug that point into the function for t. And finally, last but not least, let's say we want to find the acceleration. Well, all you have to do is take the derivative of velocity. So for I, your acceleration is simply going to be AW, or omega I should say, times negative cosine, because the derivative of cosine, or the derivative of sine, is cosine. And I probably should explain that the derivative of cosine is negative sine. That's how we got the negative sign in velocity. And then we keep the negative sign because the derivative of sine is cosine, not negative cosine. And negative cosine, keep the inside function the same. And then same as velocity, we want to multiply by omega because of chain rule. So it would actually be amplitude, to simplify, it would be amplitude times omega squared times negative cosine of this function. And then, same as velocity, you can plug 2 in and get the acceleration at t equals 2, or any point that you want to check. So yeah, here's our work. There's a lot of things that you can find with one equation for simple harmonic motion. Now, to end off on a more simple problem, we are going to be given a max acceleration of 7,500 meters per second. Then we are going to get given amplitude of 0.003 meters. What we need to find is t. We need to find the period. Now, to do this, we are going to have a max. It's going to be equal to omega squared times a. To solve for that, we're going to have 7,500, and it's going to be equal to amplitude, which is 0.003, times angular velocity squared. So if we divide both sides by 0.003, and then we square root both sides, our angular frequency is going to be 1581.139 radians per second. Now, to simply find t over here, all I need to do is do t equals 2 pi over angular frequency, and plugging this value in right here, our final answer will be t equals 0.004. Hey, good morning. I was about to get the answer.